Algebra 1, Section 8.8, exponential growth and decay. Starting with a formula, y equals ab to the x, which is something that we had some exposure to in the previous section. This is the exponential growth and also the exponential decay formula. A is the starting amount. B is what we call the growth factor. If it's greater than 1, I'm basically just reading right here. If B is greater than 1, it is the decay factor if B is between 0 and 1. That's what this inequality says, that it's greater than 0 and less than 1. Just real quick, let's investigate what the other possibilities of B could be in case somebody wondered about that. What if B were actually equal to 1? Okay, so what I'm saying is between 0 and 1, that's covered. Greater than 1 is covered. Well, what about less than 0? What about 0 and what about 1? Let's take 1 first. What if B were 1? You see, if B were 1, then the number that I plug into x really doesn't matter, right? If I plug in the time periods, and the time periods that have passed are 1, 2, 3, 4, 50, 51, 100, 1 million, 1.5, 2 3/4, doesn't matter. That 1 is being raised to that power. That's going to continue to be 1. So your starting amount then is just going to get multiplied by 1. If we're just multiplying by 1, we don't have exponential growth or decay. What we have is a horizontal line. Okay. What about 0? What if B were 0? Well, we know that raising 0 to a power is going to be 0. And for that case, again, it's not going to be exponential growth or decay. This is something that we just don't need to even consider when it comes to this concept. And then probably the most common question that I get is, what if B is negative, right? What if B were less than 0? And you know what? That's a possibility, not for this section, but certainly B could be a negative number, in which case you're going to see a geometric sequence like we studied just a couple of sections prior to 8.8, in which case the outputs are going to alternate positive, negative, as you let x be 1, 2, 3, 4, 5. So this would generate a geometric sequence where the input and output are, where the output is alternating positive, negative. Okay. Now that's not going to be exponential growth or decay either. We should be looking at a graph that isn't jumping over an axis, up and down, but rather than that is something that's approaching 0 essentially in either the positive direction or the negative direction. Negative direction if it's exponential growth, meaning that it's going in the positive direction, it's going upward to infinity. And exponential growth is as x gets bigger, our output is getting smaller and approaching 0. Okay, that is, of course, if the graph is not shifted, which is not even going to be, shifted graphs are not even going to be a concept for you all in Algebra 1. Okay, so that's that formula. And a couple of examples for you. It says in 1998, I might make fun of these examples a little bit. 1998, that was only 22 years ago. In 1998, a certain town had a population of 13,000 people. And since 1998, the population has increased at 1.4% a year. And they want us to write an equation to model the population increase. Okay, so this is of the form y equals ab to the x, as everything we discussed today will be. And it's increasing. That means that it's exponential growth. That means the b value we can expect to be more than 1. And actually, we can figure out what that is based on this number that they gave us. Okay. Now, very important that you change percent to decimal. 1.4% is, as a decimal, 0.014. 0.014. And as we've discussed a few times now, that b value is going to then be that number that I just stated as a decimal added to 1. So really it's 1.014. Okay, so if A is the starting amount and they told us we had 13,000 people, and B is what we just said to be 1.014, this is an exponential growth formula that'll calculate the population. Okay, so that's what they asked for in A. Then they'll ask us a question in B. And again, it's kind of funny because it dates how old the textbook is here. Use your equation to find the approximate population in 2006. I suppose when this book was new, 2006 was in the future. But now it's well into our past. And anyway, it was a fictitious town to begin with. So think about that. From 1998 to, was it 2006? 2006. From 1998 to 2006 is 8 years. Now, here's something that I have talked about before, and I pretty much talk about in every one of my classes, which is when we ask you for an equation, which this problem did, there should be two variables, input, output, x and y. Okay, don't put the 8 here. You put the 8 here, you now have an unsimplified number, right? 13,000 times 1.04 to the 8th is a number. In fact, we're going to figure out what that is. But that's going to be part B. In part A, we want the equation. If you want to show me what you're plugging in, that's great. Use it with an arrow, okay? Show that with an arrow. Oh, we're going to plug in 8. We'll plug in 8 for x. Here's the x that's showing in my equation because that's the input. And then we would use our calculator to actually do 13,000 times 1.014 to the 8th power. I did this already to check this answer. This is correct. 14,529 people. And I remember when I did it, it was like 14,529.3, okay? So easy to round down. And here's the thing too, another kind of just a side note, maybe a preference thing for me. You know, if your Algebra 2 teacher next year says something different, you do what that person tells you to do. But to me, it's just easiest to round to the nearest person. A lot of people, even if they got, you know, let's just suppose this answer was 14,529.9. Well, they'll still tell you to round down because you can't have 0.9 of a person. Therefore, we're going to go down to the next whole person. It's a small point to make, but I think just round to the nearest person. If it was 14,529.9, my answer would be 14,530 people. Just round to the nearest person. It makes it easy. Here you also have a little bit of an unrealistic or an example that I could make fun of. Suppose you deposit $1,000 in a college fund that pays 7.2%. interest compounded annually. Find the account balance after 5 years. Now again, this is y equals ab to the x, which would be y equals the starting amount, which they said is $1,000, times b, which would be 1.072 to the x. A lot of times I find for students that the hardest part is coming up with that b value. Change this to decimal, 0.072, and then add it to 1. 1.072, okay? And I don't remember what that answer is, so I'll do that real quick on my calculator. Because we are going to plug in 5 for x, right? I have x in my equation, but then I'm showing that I'm plugging in 5, and it comes out to $1,415.71. Now, as far as rounding goes on this type of problem, when it's money, round to the nearest cent. That's hundredth of a dollar or nearest cent, and that would be 71. Okay, now again, you might have a teacher in a future year that says, well, you know, round down unless you get that next cent. So when I get 1415.708, somebody might tell you to just round that to 70 cents because the bank doesn't give you the next cent. That's fine. That's one way to teach it. I just think it's just easy if you just round to the nearest, right? Then we're all doing the same thing. So I get $1,415.71. And what's funny about this example then, of course, is what does $1,415.71 get you in college money today? Like half of one class, maybe? Okay, so then that brings us to what's known as compound interest. So the second part of my notes here, and I'll try to break all this down for you. A equals P times the quantity 1 plus the fraction r over n, and then that parentheses is being raised to the power of the product of n and t, okay? Now, P, as I have written over to the right here, is principal. I also had to look up the spelling on this one. That is spelled correctly. And principal means starting amount, okay? So if they say you are investing this much money at compound interest, that's the number that goes in for P. R is the rate as a decimal, okay? So again, just to use the previous example, if they said 7.2%, this number would be 0.072. The decimal, don't add 1 to the R value because the adding 1 is already occurring here, okay? So this is just the rate as a decimal. N is the number of compoundings within a year. So a lot of times you'll hear of bank accounts that compound monthly. That's pretty common. If it compounds monthly, that means 12 times a year, your N value would be 12. Your N value would be 12. And it goes in two places, notice. It's the denominator of the fraction, then it's also a multiplier in the exponent. And then t is in years. And the reason that I didn't list that over here, but rather have it the green pointing at it and saying years, is the same reason that I did amount here and the same reason that I did time periods up here, is I do want you to realize that that's the variable, right? Principal, the one, the rate, the number of compoundings, which actually occurs twice, those are all values that you'd be given. Those are constants. The number of years can change. And of course, based on that, the amount can change. So amount is dependent on the number of years. We still have an independent, dependent situation. T is independent. Amount then would be dependent upon that. Now, before we go ahead and just finish out the rest of the examples, I do want to make the case that this is y equals a b to the x. Okay? It looks very different, but it is still compound interest. It is still in that form. And obviously, I won't cover this, but just for a second, capital A and y, those are just the output variables, dependent variables. T and x, they are also variables. But the full truth is then that x would be n times t. Now that's okay, right? If I have x, which stands for the exponent, and in my compound interest formula I have nt, where n is guaranteed to be a number, well, I'm raising it to this power. And whatever t is, it gets multiplied by n, and that's the power that is standing in for x. Okay, and then what's left then is, of course, lowercase a and p. Those are the same thing. In fact, I've already really have used the right verbiage for that in this video. P is principal. That's what you're starting with, and a has always been the starting amount. So then finally, what is going on in the parentheses? The b value, the growth factor, or decay factor, but in the case of compound interest, it's going to be growth because you're adding it to 1. The b value is 1 plus r over n. And that, again, that's going to be a number that's greater than 1. Think of a rate, again, let's just use simple numbers. Think of a rate of 12%, and then you're compounding monthly. Well, 12% as a decimal is 0.12. Divided by 12 compoundings in a year, 0.12 divided by 12 is 0.01. So you're getting 1.01 times your principal. But now that seems like it's not to your benefit. You'd rather have 12%. But that number gets put back in as an exponent, so it ends up getting multiplied by 1.01 12 times as many times as it would if it were annual compounding. And if you test this, and we will in just a second on the example that we just did, we'll test this with compound interest, you'll find out that compound interest is to your benefit. Of course, it's to your benefit if you're the investor. It's actually to the negative if you are the credit card consumer who's paying credit card interest. That's an argument against using credit cards. Okay, so back to an example then. Suppose the account in the above problem paid interest compounded quarterly instead of annually. Find the account balance after 5 years. Okay, so we were asked that question about 5 years here. Now we're going to do that again, but it's going to be compound interest. So let me just write the formula again real quick here. And all the information given would be like this. It was $1,000 times 1 plus the rate was 7.2%, so 0.072. Quarterly means 4 times a year, so you're going to divide by 4, and that number would go here as well. And then T is our output. And then we're going to be plugging 5 in for T. Now, if you're going to type this into your calculator, you do want to be careful that you don't mess up an orders of operation. We're plugging in 5, right? And when I do all of that, I get $1,428.75. Again, rounding to the nearest cent. 1428.75. Okay? Now again, a bit of a silly example. It probably would have been better if they'd used 10,000 rather than 1,000. But this is the number they give us. And what they want you to do now is compare the numbers. Okay, you got 1428.75 when it was compounded quarterly. You got 1415 when it was compounded annually. So it is to your advantage more compoundings. If you did this monthly, real quick, it would just look like this. 1,000 times 1 plus 0.072 over 12 to the 12t. And if you plugged 5 in here and did this, you'd get yet more than 1428.75, right? The more compoundings it would be, the better for the investor. All right, a couple more examples then. This is known as half-life. The half-life problem is also an exponential growth or decay problem. And in fact, because it's half, it's going to be decay. And it says, suppose a lab has 80 milligrams of this thing called technetium-99. Now, to be clear, the 99 has nothing to do with the problem. That's just a number that helps identify which isotope we're talking about. Technetium-99 is a particular isotope that has a half-life of, notice it says 6 hours. Okay, now here's the thing, and I'm going to give you 2 ways to do this. Number one, you can keep it simple and keep it y equals ab to the x. Okay, and when you do this, it's very, very simple to come up with the equation. A is the starting amount. They told us we had 80 milligrams of this stuff, so that's going to be y equals 80 times something to the x. Now, if you thought plugging in 80 was easy, actually this is actually going to be easier than that, because for every half-life problem, make sure you hear this, for every half-life problem, the growth factor is a half. The decay factor actually is a half. The number that goes in here in my parentheses will always be a half. Okay? Basically what happens with half-life, and maybe you've heard of this in a previous math class or possibly a science class, is you have a certain amount of a radioactive isotope that is losing mass over time. And you start with 80 milligrams of something. After the course of 6 hours on this particular one, and it's different for different isotopes, right? As it can be in something measured in minutes, it can be measured in thousands of years. Okay, carbon-14, I think, if off the top of my head, is 5,730 years or something like that. It's over 5,000 years. That amount of stuff will get exactly cut in half over that time period. Okay, so for this example that we have, 80 milligrams in 6 hours will become 40 milligrams. And then 6 hours after that, 40 milligrams will become 20. And then 20 after 6 hours will become 10. And it's not linear, it's exponential, because 80, 40, if it were to stay linear, would be 0 after that. 80, 40, 0, and then you'd be done. But no, half-life just takes itself and cuts itself in half every, again, in this case, 6 hours. So 80, 40, 20, 10, 5, 2.5, 1.25, and on it goes. Okay, now if you do it this way, and I'm not trying to steer you one way or the other, but if you do it this way, then the challenge becomes, what do you plug in for x? Let's read the question again. Technetium-99 has a half-life of 6 hours. Suppose a lab has 80 milligrams of technetium-99. How much technetium-99 is left after 24 hours? The question becomes, how many 6-hour half-lives fit into 24 hours? Okay, and that answer would be 4. And the way you got 4 was you went 24 divided by 6. Okay, if you were here and you could see me, I put my hands out and I say, here's a 24-hour time period. How many 6-hour slots figure into this 24-hour time period? Okay, in fact, I just did those motions, but you weren't here to see it. So anyway, you're going to quickly do this on my calculator. 80 times 1/2 to the 4th power is 5. Okay, so that's what you would have left is 5, and that's milligrams of technetium-99. Okay, now there are 2 ways to do this. Another way to do this would be to go like this: y equals 80 times 1/2 to the x over 6. Okay, and in this case, what you're doing is you're accounting for the half-lives. And the benefit to this, and I'm not trying to steer you one way or the other, the benefit to this one is that now you're just plugging in the time. All right, so that's going to be 24. It's essentially the same calculation now, right? You're taking 80 times 1/2 to the 4th power. The difference is simply, do you want to keep the equation simple, y equals ab to the x, and then have a little bit more thought in what you have to plug in for the time periods? Or do you want to have a little bit more thought into the equation? I believe this is the way the book does it. And then you're raising that to the x over 6 power. I apologize if that doesn't look like an exponent, but this is x over 6 is what 1/2 is being raised to. And then once you do that, well, you know the time periods that they gave us to be 24 hours, that's getting plugged in for x, okay? And then either way, it's going to produce 5 milligrams. Now, one other thing about this example, let's just kind of multiply it out. You started with 80. After one half-life, you have 40. After two half-lives, you have 20. After three, you have 10. And after four half-lives, you have 5. Yes, this is a geometric sequence, okay? And it's why this all fits well into chapter 8. So we just found a sub 5, if it were a geometric sequence, to be 5 milligrams. Okay, one more example. Back to population. We started with a population example where it was humans and it was increasing. Now it's animals and it's decreasing, but the concept is still the same. The main difference here is now it's decreasing, okay? Endangered species, it's losing 2.4% per year. And suppose there were 60% of these animals in a given area in 1999. Write an equation to model the number of animals in this species that remain alive in the area. Okay, so again, it's y equals ab to the x. And as I said earlier, a lot of times what the difficult part is coming up with what goes here in the parentheses. What is the growth factor? Or in this case, it's actually the decay factor. What goes in those parentheses? If we're losing, now listen to this now, if we're losing 2.4% per year of this particular animal, we're keeping 97.6% of that animal, all right? And again, it's a lot of times it's right here where students don't know what to multiply the 60 by. You got to process what that decimal is, what the percent is. We need it as a decimal, and then we need to take that out of 100. You see, in the exponential growth example, you're adding to 1. Here you have an exponential decay example, you're subtracting from 1. And I can do that as percents. So for example, if I take 60 and I just multiply by 100%, 100%, 100%, 100%, you're just multiplying 60 by 1 each time, you're going to remain at 60. That would be like an exactly stable population. It's not increasing or decreasing. If I multiply by more than 100%, that decimal would be 1.0, whatever. Here we're actually going to be multiplying by something less than 1, less than 100%. It's actually 97.6%, which as a decimal is 0.976. 0.976. Okay? And that's part A. That's the equation that they wanted. And in B, they're going to ask us about how much is left. 2005. Okay, so this was 99 to 2005. So that means 6 years later, we would be plugging a 6 in here for X. And then we could do the math on that. I'll do that real quickly on my handheld calculator, which is 51.86. So I'd say 52. 52 of these animals. All right, again, just rounding to the nearest animal. All right, thanks for tuning in. Good luck on your homework.